I'm also from the other side of Green Street, so very nice to be invited and have an opportunity to talk a little bit about our perspectives on data. What you're going to hear is a little different because our approach is our object of study are data and the people who create and use them. And so just to put this a little bit in the current national context, many of you who generate your own research proposals know we now have requirements for data management plans that have to go with proposals. There are many, that's with NSF, NEH, NIH, all the various agencies are falling into place here. But in addition to that, there's a lot of effort in this area. So there's a recent Office of Science and Technology policy memo that came out of the White House in February, where 65,000 people, scientists, publishers, members of Congress, and the public signed on to say, we want access to not only the publications for research, but the actual digital data. And so there's a lot of movement in this area. Federal agencies are now going to be required to have clear, coordinated policies for increasing access. So our job is really to understand how do we get there? How do we get communities ready to share their data because they're going to be expected to? So I know this concept isn't familiar to everyone, so I just wanted to give you a quick background. Our definition of data curation is the active and ongoing management of data through its life cycle of interest and usefulness to scholarship, science, and education. There are many definitions out there. Wikipedia has happened to pick up ours, so it's getting a lot of play. But I really like one from the Digital Curation Center in the UK. It's really focused on the notion of fit for purpose. Curation being about making sure data over time are fit for new purposes. A lot of people associate the term with Jim Gray from Microsoft Research, who was working with the Sloan Digital Sky Survey group back in 2002. They did a nice paper on the issues of preservation of that huge digital object and resource, and talked a lot about the necessary role of really capturing all the possible metadata, including project designs, documents, discussions, procedures, software, everything else. But in fact, the notion really dates back to science and natural history museums and the curation of objects for study in science museums. You can go back to a paper in Nature where the curator of the British Museum of Natural History is starting to allude to this need for really big data, what they considered big data then, and trying to manage it and making it useful, justifying the investment in it. Then DOE in 1994, in one of their first bioinformatics summits, when they're talking about bioinformatics, really invoked that metaphor of curation from the museum community and called for data curators to be the new profession for playing this role. And then there's some other very nice papers that have come out of the museum community. So while we've done a lot, in fact, we've been involved with curating the Sloan Digital Sky Survey recently, most of our research right now is on what's called the long tail of data. So there's been some predictions that the long tail is going to be 2 to 3, or is 2 to 3 times larger than big data, the stuff that comes off of instruments and is generated pretty readily. The claim is, it's a lot easier to handle, understand, and archive data, big data, because it's more homogeneous. And in fact, small data, or the long tail, actually has been a huge investment. So finally, we've been saying this for a long, long time, but one of my colleagues finally, when he was a program officer at NSF, was able to do an analysis of all of the proposals over a given year to show that 80% of the proposals were really single PI, small group science, not necessarily generating any big data, and sort of under this $300,000 range. Not as big in total dollars, but a lot of projects, a lot of people, a lot of data coming out of that. So when we think about curation, or at least this is sort of the groupings that I've come to associate at a very macro level, you hear a lot of talk now about curation in order to retain the scholarly record, in part for reproducibility. A lot of this gets talked about in terms of climate modeling and climate change. And it is often thought about as data that's directly associated with the production of papers, models, other products. But in fact, there's a lot going on and a lot of interest in data in terms of it as research capital. So I think about this as producer value, and and institutions are getting more invested in being centers of excellence for certain kinds of data, for certain kinds of research. And then also even more so interested in just the raw materials of research. This is the consumer value of data. So, and we're working very closely on some of this to develop repository services for data sharing and data reuse. So the two projects I'm going to talk about and just introduce you to are the Data Conservancy, and that is sort of closing up, although there's some new work going on there, and the Site-Based Data Curation at Yellowstone National Park. So the Data Conservancy is a big collaboration. It was one of the 5 awards that was through the NSF DataNet program. It's part of the cyber infrastructure for 21st century. So about $9 million for a national scale infrastructure for this project. It's led by Sheridan Libraries at Johns Hopkins, and the PI is Saeed Chowdhury. I was a co-PI, and there were also co-PIs at Cornell, NCAR, and Marine Biological Lab. So the Data Conservancy is basically a community that develops solutions for data preservation and sharing to promote cross-disciplinary reuse. And so for us, when we say preservation, we mean not just saving the bits and the bytes, but really requires providing enough representation information, context, metadata, fixity, etc., that someone other than the original data producer can use and interpret the data. So we have 2 teams at Illinois working at this project. I'm going to talk mostly about the data practices team. We do qualitative studies. We're social scientists. We're studying the long tail, complex, heterogeneous data, reuse value, and things like that. Second group, Data Concepts group, is led by Alan Rainier, who I didn't know was here. He's back there. They're studying formal terminology, identity conditions for data sets, versions, etc., representation levels, and such. So over the course of this project, we've been investigating across domains, and we've been covering earth and life science. So you see the ones up there on your left are what we covered in Data Conservancy, but in fact a previous project allowed us to bring other domains into the picture to get a better sense of the comparative analysis that we were doing. And again, you might not be too familiar with these kinds of more qualitative social science approaches, but we had to, it's really hard to get scientists to talk shop about their data. They take it for granted, it's very mundane. They want to talk about science research questions, which we enjoy, but we want to get down to the data. So we had to come up with some techniques that really get us there quickly. Because we don't want to waste their time, we get a couple hours, and sometimes follow them around if we're lucky. So we start now with lead scientists, PIs. We get in with them. We start with a pre-interview worksheet to get them focused on a project and certain types of data that we're interested in. We move then into semi-structured interviews, and then we do follow-up sessions with particular people who tend to be very reflexive on their data. And then we move on to the people who are actually working with the data day to day. The researchers managing the data. That's often postdocs or research scientists, graduate students. They understand a lot more about the stages, the versioning, the standards, the tools that are at play. And so then what we do, we write our own papers and do our deep comparative analysis. But in the meantime, we want to push as much as possible back to the infrastructure team at Johns Hopkins, where they're building infrastructure and interfaces and all of that. So we set up a rapid reporting framework for doing that, where we would analyze the qualitative data very quickly and push these key observations back that had implications for metadata, policy, other things that were going on there. Now, as you can imagine, we are challenged by the fact that we hear a lot of things that we have to interpret. So we hear scientists say all the time, of course I'm willing to share my data publicly. And in fact, sometimes they do, but they have one bad experience and then they stop. They say things like, there are no standards in my field. No data standards, no metadata standards. Well, we know that's not true, but from their perspective, it's true. Or my data will never be of use to anyone else. We hear this all the time, but yet we can go somewhere else across campus even and see an opportunity where data could play very nicely for answering the questions there. So one of the early observations we made is most of the forms of data that scientists are willing to share are not the ones that are most valued for reuse. So a lot of what we're doing now is how do we get scientists working in a way, get their workflows in a way that they can be producing reusable data. materials of research, that's of application to other fields, that can be integrated, aggregated. At the same time, we have all these stories about, and more worries than we have real cases, but worries and concerns about misinterpretation, misappropriation. We do have cases of, good faith efforts not being followed when data are shared. So there are real concerns, a lot of legitimate ones, but a lot are worries that we're not so sure are going to come to be true. So again, we were talking, as I mentioned earlier, we're interested in both the producer and consumer sides. So we've been looking a lot in early years of the Data Conservancy on utility for producers. And again, looking at small science where it's very complex, this often means bringing together lots of different kinds of data into some kind of unit that they feel is essential for understanding the science and for reuse of their data. So in the area of geobiology that we've been studying, we call these units site-specific time series, and they tend to include things like spreadsheets, which themselves are aggregates of many different kinds of data, but also microscopy images, field, lots of photos, lots of annotations on the photos, microbial genomic data, etc. That's just a subset. In volcanology, another area we've looked very deeply in, we call their units rock profiles because they start out with the physical rocks they get from the field. They do sampling and sectioning of that. They then digitize those, but they also have chemical analyses, photographs, field notes, etc. So, and then just to note on the bottom, there's no sharing conventions for any of these in these particular communities. It's often by request, usually after they've already made their publications or made their stamp on it, and no real repositories where they feel their data can go except for the genomic data. So again, for us as trying to educate and do research about what the actual curatorial tasks will be, we map out what parts of those data need to be put together in what ways, how they need to be preserved, how they need to be related, what the provenance is. These are the kinds of curation tests that you can't read, probably, but the identifiers, the linking, how we provide access, how we manage provenance, etc. But in fact, the other thing we've really looked at is where do we see the utility for the consumers here? Because it's a great, huge investment to curate those very complex sets from the perspective of the producers. At the same time, we're getting evidence that parts of those data are very valuable for other communities. So utility for consumers is a very important issue. So what's the most reusable component? Well, right now it looks to be those chemical analyses in the spreadsheets, for instance. So we see lots of evidence of the isotopes, the iron, the titanium oxides. We don't care about them, but we know others that would. And that, in fact, the geochemical data does not require necessarily the same kind of reliance on the field context that we see in geobiology and volcanology, for instance. So the real challenge here, of course, and that we're trying to get a handle on is anticipating what those other communities might be, because you have to curate it in a way that it's actually usable for them. So tracing this, we know that with the geobiology time series, we know who the designated communities are in the OAIS sense, the original communities. And then we come to learn more as we learn more about the use, etc., about the potential communities. Now, once we have big repositories with lots of use, we can track these things easily. But right now, we have to find other means of sort of tracking the potential users. So chemistry, evolutionary biology, bioprospecting is very big with some of this data, the pharmaceutical companies in particular. The U.S. Park Service has a great interest in a lot of the geobiology data and public health. This is a real case where microbial data wasn't the original intent of the data, but was able to use to find the presence and extent of disease in certain animals and the risk associated with that then. Same with volcanology. We know the original designated communities, but then glaciology was able to take the field photographs and assess spatiotemporal glacier change over time. Lots of interesting results on climate change there. So, emerging questions for us are, what do we know? What data do we invest in? And can we anticipate value over time? And so thinking about that glaciology example, our colleagues at National Snow and Ice Data Center say this is a classic example where the glacier photo collection, which 10 years ago nobody knew about, and no one thought it was worth investing in digitizing it is now their second most popular data set. And they have some very popular data sets. All the AP journalists go there. But they also have noted, it's more anecdotal at this point, that there's these 30-year peaks of use. And so they've been sort of tracking, in a way, and we have some data that we can analyze, I hope, that data will go in, and it's used a lot when it's first released, but then about 30 years later, it becomes high interest again when there's real other comparative data that comes in. Other really big questions. So our colleague at the National Research Council wrote a paper that we like a lot, but he makes this claim: the value of data increases with their use. Well, we like that idea, but we also wonder, is this true? If it's true, how do data actually gain value through use? Can we document it? So we sort of tried to go after that with some of the data we collected from these particular communities. We were able to go back to the climate of soil, volcanology, sensor, and stratigraphy, and sort of get a sense, try to get a sense of what are these real indicators of value based. Again, this is from the producer perspective. So the first three, not so surprising, I guess. Reputation of data collectors, spatial coverage, longitudinal coverage. But the next set is really interesting to us. Unique conditions, data areas that are rarely studied, politically volatile areas, or data, and data that requires permitting in order to get access to it. So very high value, a little more scarce. But the next sets are really important as well. Multiple sources for triangulation and context, and then data with documentation of workflows and conflicts. So these are things that we know are high value. And then we went to try to really think about this idea of gaining value. So can we see when and how data gain value through reuse? And this is just three little scenarios that we were able to track. So the first case is where we saw richness and verification through reuse, reusers getting complementary evidence to bring to bear. So ocean modelers working with field campaign data, going out and trying to find additional data on the weather during the particular flight patterns at the time, the actual satellite serial numbers, looking for irregularities in open sea mooring. And as they do that, they're, again, building these, refining the data, but also bringing other data sets that have important complementary content. We see other cases of refinement and fit. This is a group of sensor engineers that transformed a set of data several times for different audiences. So reworking water measurements to share with search and rescue teams, triathlon organizers, fishermen, and even the ship industry. So lots of reworking of the data for different audiences. Now they have versions that are of interest. And the last one we don't understand quite as well yet. This is sort of a case of recalibration and feedback. Some rainforest researchers had gotten some block sensor data and wanted to know more about the original measurements, went back at the instrument level calibrations, and then sort of packaged that up again and sent it back to the original providers, which was kind of a nice feedback there. So for us at the Data Conservancy, there's some lessons here as we know more about the value and what happens with reuse. So what are the implications for the data services they're trying to produce? Well, you might want to actually recruit data with multiple indicators. At minimum, you can sort of assess what's coming at you and set priorities based on that. You want to anticipate and track long-term reuse cycles, because if it really takes 30 years to get the improvement in the data, it might be worth waiting for and catching it when it happens. Promote reuse to increase the value, and then you have to find ways to capture and represent the reuse as it accrues. Okay, so I wanted to take a few minutes to talk about the next project we're on. I just got back from the first workshop we held with the stakeholders in this project. It's called Site-Based Data Curation in Yellowstone National Park. It actually grew out of the Data Conservancy work with the geobiologists. Co-PI is Bruce Bauk on this campus in geology, microbiology, and biology. We also have a co-PI at Yellowstone National Park in Rodman, and Saeed Chowdhury, the Data Conservancy. And here we're just really focusing on developing a framework of policies and processes for curation of research data generated at scientifically significant sites. And Yellowstone's our model site for that. And then within Yellowstone, systems geobiology is the exemplar case. in particular, beginning by starting on the microbial data, because more than 50% of the data, the permitted data that comes out of Yellowstone right now is microbial. So this is important to us. It's a really nice intersection of earth and life sciences. Yellowstone's a mecca for geobiology data collection. The people doing research there are studying everything from the origins of life on Earth to life on other planets. And what we realized later, after the fact, is that there are the multiple data value indicators going on with these data. Longitudinal coverage, very unique conditions, politically volatile, and permitting requirements. Not everybody gets to go. Scientists want to go year after year after year. And lots of multiple sources for triangulation and context. So very important for both Yellowstone in terms of their resource management. So they want to be investing in strategic science, but they don't have good ways of tracking what happens over many, many years. And the researchers themselves know that many people collect data at that particular hot spring or that geyser or that particular vent at that hot spring, and they want access to it. It's been going on for decades and decades, and they don't know where it is, but they know what they could do if they could find it. So we're there to help them get there. So get a sense of what we're talking about. This is just a description of one scientist's hot spring data parameterization. So rock deposits, water, microbes, climate. All of them, interestingly enough, include photography. And after this workshop, we've really come to realize where we thought photography was probably low priority. We now think it's really high priority in terms of if we're worried about context, if we're worried about bringing data together that help people understand context, it's going to be high priority. And at the bottom, it all includes modeling, and it's then everything in between to get to the modeling. Are we running short on time? I know we were. Okay. Well, I cut out a few slides because I thought we were running short, but I know I was also asked to maybe talk a little bit about our education programs, so I'll do that. The research that we're doing in these two and other projects is feeding directly into our specialization in data curation in our Master's in Library and Information Science. We started that with a grant in 2006 in the sciences, and then got a parallel effort going in humanities. And so we've been graduating students since about 2008 with specializations in data curation. They're going to data centers, research centers. They're also going to research libraries, large museums. They're going to the private sector. They're going a lot to the public sector. People are going to the FBI, to city governments, public broadcasting, those sorts of things. So everybody needs to take care of their data and make it work for them, right? There's a big demand here. So you got in the business at the right time. But I want to talk in particular about the most recent effort in what we call the Data Curation Education and Research Centers. This is a collaboration with the National Center for Atmospheric Research, who was a partner on Data Conservancy. And we're also partnering with another iSchool, which at the University of Tennessee. And we're taking our core curriculum in the specialization of data curation, making it available across the schools. It's a distance program, so it's easy to do that. But the biggest component, the thing we're most excited about, is the field experiences for the students. So we're putting master's students there for 7 weeks for summer internships. We're putting doctoral students there for 2 semesters to really look at the research problems coming out of these big, state-of-the-art data management centers. And the best thing is we were able to pair students up with 2 kinds of mentors. A data mentor, someone who's involved with the day-to-day data management, these very large, things that everybody we're talking about today. Even some of the big climate models are all in the U.S., and the biggest ones are at NCAR. But in addition to the data mentors, we're also pairing them with the science mentors. So someone who's there actually conducting science on those data. And again, this is how we've constructed our program. It's very much about how you are partners in research with scientists, working alongside them in order to get to their, help them achieve their scientific goals. So NCAR is helping us do that with the internships as well. There's a video you can watch that explains a little more about this. So internships are very important. They're difficult to arrange, but we've been doing a pretty good job. These are the internship sites and practicum sites we've had for students over the years. Not every student gets this opportunity, but we have many more opportunities, and we have students willing to go. Most students, these graduate students don't necessarily want to pick up and move somewhere. in scientific centers or big libraries or big research centers, or even small ones when it makes sense. So these are the kinds of positions that students are getting. As you can see, they haven't come together in any kind of real uniform way. As was mentioned, I'm on a National Academy of Science Study Committee that's trying to understand the career trajectory for these kinds of roles. There'll be a report coming out in September, we hope, that will try to explain what's happening in science, what's happening in digital and data curation, where the convergence needs to happen in informatics and elsewhere, so that we can get a little more coherence and better, broader education across the country and elsewhere. Okay, so I'll finish there, and happy to take any questions you might have. What level? So, yeah. So the levels, I took that slide out. Yeah, so in fact, the workshop we were just in was helping the scientists understand. So NASA has levels, levels of processing. So it starts from the raw data all the way on to the models, and there's 4 levels in between. We try to get scientists to understand. They just think of it as, I transform my data, or I process my data. Which one do we keep? Which one do we preserve? We try to get them to think about what's the most shareable, useful one. And so part of this workshop was exactly trying to get them to stop thinking about, I need to produce this table for my publication, to I need to submit a data set that's coherent, and well described, that can be used by someone else. And so in oceanography and other areas we've seen the communities develop their own levels of understanding. We're trying to put geobiology into that course. That's an excellent question. I mean, it really is about understanding what point do you capture that and which of those are the most shareable.
Okay, any other questions? So if not, let's thank the supplementary. So we have one last thing. So before we do that, I need to step out. I need to find out who won, because I don't know who won. Right. So give me a second. I'll be back.